Okay, as promised, let's prove how we get the centripetal acceleration equation and from that the centripetal force. So let's see how that works. We'll call this proof of centripetal acceleration equation. And that's the v squared over r. So we'll start off with the circle. And so we've got this circle and we have a velocity here. We'll call that v1. And the velocity here is, we'll call that v2 at that point. And let's say we're spinning this around our head, over our head. It's not a vertical circle. It's spinning over our head in a horizontal circle, and the object is spinning around and in this direction. So if it's spinning around at a constant speed, let's say the speed of the object equals 2 meters per second, how do we get acceleration out of that? Acceleration is a change in velocity, isn't it? Well, if the speed is constant, how is the velocity changing? Look at the diagram, and what is changing about that velocity? If you said direction, you're correct. Velocity is a vector. And vectors have magnitude and direction. So it has magnitude, that would be 2 meters per second, and it has direction, which, and you can see which way they're pointing. V2 is pointing straight downward, V1 is pointing into the fourth quadrant, if you will, or down into the right. And because of that, we can see if you change speed, that's what we're used to, change speed, and you accelerate or decelerate, negative acceleration. But now, because it's a vector, we can also say that if you change direction, you also accelerate. So now we have another way of accelerating, and we've changed direction. Now let's see how that works. So I've got the two arrows up there. I'm going to use vectors. We're going to use graphical vector techniques, but we're not going to do this literally or mathematically. We're going to kind of do it by kind of qualitative, in a qualitative sort of way. And you can see V1 is pointing down, V2 is pointing down. Let's look at our definition first of acceleration. Our definition of acceleration way back is delta V over delta T, which is equal to V2 or minus V1 or V final minus V initial, like that. So what I have to do is, clearly I have to subtract. If these are vectors, I clearly have to subtract V2 vector from V1. And we can do that graphically. We can do that using vectors if I add them the way you typically add vectors. So I have vector V1. Let me do that in red. Vector V1 pointed down roughly this way, and I will scroll back up. You can see that it's pointed approximately in the same direction as that circle. And I have vector V2 pointed straight down. Now if I add them, it would just be V1 plus V2, but I want to subtract them. So I've got to make V1 negative. And if you remember how to do that, you just point it in the opposite direction. It's 180 degrees from where it is, and that would be a negative V1. So now I can add using vector graphical methods. I'm going to add v1 and v2. v2 goes straight down. Okay. And now I'm going to add minus v1, and we add it going off in that direction, just like that. Now, the vectors are the same length. Remember, they have length and direction. Since they're both 2 meters per second, the vectors are of the exact same length. What's different is their direction. And so when you do that, you then add them, and this is the sum of vector. This would be v2 plus a minus v1, or just v2 minus v1, which equals the change in v. That's how v changed. Now, what's interesting about this is look at the way it's pointing. We drew our circle. I'll go back up there again. There's our circle, and it's pointing inward. Let's draw the circle again. Here's my circle. Not a great circle, but there it is. V1 points like this. V2 pointed like that. V2, V1. Delta V, the change in V, and I'm going to pick it right in the middle, right between two vectors. You can see which way it's pointed. It's pointed directly towards the center, right? Center seeking. That's the change in velocity. Remember our definition of acceleration, delta V over delta T. And time is a scalar. The change in velocity is a vector. So all I'm doing is dividing a vector by a number. And so I get the same direction. A is in the same direction as delta V. Therefore, I can also write A. So we can see the acceleration does point into the center, just like the force did. All right, so now, well, now I've proven that I can use vectors to do that, but, you know, and you can use vectors. You can use, let's say, ij vectors, unit vectors, add them up. If you've got the data for it, you draw your circle on a graph, you write up your vectors, and you'll get the answer. But that's not very convenient. I want to do this geometrically. So in order to do this geometrically, we've got to take our vectors there, and I'm just going to erase this a little bit here. And we're going to put in a radius here, r, and a radius to this vector here, now r. Now remember, these are tangents, and so these are perpendicular to that. The angle between these two we'll call theta. And joining these two, we're going to draw this line here, which is called a chord. Okay, in fact, let me make that a different color there. That's the chord. We're going to call that x. That is, those two sides are the same. So any triangle that has two sides that are the same is called an isosceles triangle, right? And so I have r, and x giving me an angle theta. Well, I won't go through the proof now. It would take too long. But the angle theta here, we need to do that. The angle theta located right here is equivalent to the angle between these two velocity vectors here. That's, as you can see, if I were to draw this one straight out like that, it would be equivalent to this angle right there. You can prove that. That would be the same there. You can prove that. You can see that both radii are perpendicular to those vectors, and so you can look at some geometric proof for that. But to save time, we'll just say that they're equal. And the setup I have is I have V1 and then V2. But remember, they're the same length. They are the same length. And the base of that triangle, so I'm going to call that V and V. And the base of that triangle was my change in velocity, delta V. And now I claim that that angle is the same. Well, I have two triangles. They're both isosceles triangles. Let's see if I can actually spell this. Isosceles triangles, both isosceles, and the angles are the same. The angles are congruent. And if you have that, then you have what's called similar triangles. So we've now associated our vectors with some geometry here. And the handy thing about that is that now we can do a ratio, because since they're similar triangles, the base and the heights are related. And so we can say x, the base of this triangle, is equal to r, as delta v, the base of the other triangle, is equal to v. And you notice here, I've got delta v. I've got an expression for delta v. Here, again, here's our equation, delta v over delta t, the acceleration. Let's solve for delta v. Delta v is going to equal xv over r. Well, now I can take this and plug it in here. Some practical geometric properties of the rotation. And so I've got xv over r over delta t. Extend the page there a little bit, and then we get a equals, I'm going to drop r down. So a equals, I'm going to drop the r down, as I said. It's going to be xv over r delta t. And we're going to associate, as you know, the associative property. You have ABC is equal to A times BC. And so, and also you have the commutative property. We have AB equals BA. So we can apply these principles here. I'm going to take x over delta t and put those together, and v over r. It's really the same values. But now, what is x over delta t? You can see that x over delta t is distance over time, which is simply velocity times v over r. And so finally, we get a equals v squared over r. And that's the proof for our centripetal acceleration.